Hello and welcome back to another video with It's Dr. Dan, and what we are going to be looking at today is periodic table trends. So one thing about our periodic table, in this video, we are going to be learning exactly how it came about, why does it have the shape that it has today, and what kind of properties can you actually predict by knowing the trends of how this thing is organized. There are a lot of little hidden tools that are found within it that can really help build your understanding of chemistry to help you be able to do very, very well in your course. So in this particular video, we're going to be looking at not only how is it organized, but how we can actually see how there are different trends in here based on the direction of the table that you're kind of moving towards. So whether you're going from maybe, let's say, left to right or from up to down, up and down, you're going to be seeing different properties changing. The ones that we're going to be really looking at today specifically are atomic radius, which is how big or small these different atoms can actually be. And keep in mind, we're still talking atomic scale, so very, very tiny. We're also going to be looking at the ionization energy as well, which is how easy is it for an atom to, let's say, lose an electron, or electron affinity for how easy is it for it to actually gain an electron, right? Those trends go in the same direction. Now there's also metallic character, so how metallic is something. So the more like a metal it is, you can see that trend as well. So we're going to be looking at those as we kind of move through this, and I'll be explaining all these little details. So let's try to take a look and learn and take a bunch of good notes, and I hope that this video helps you understand all the different trends that you will find from your periodic table. All right, so one thing that we've realized through the course of many videos and all this different chemistry stuff is that the periodic table, the way that it's really been shown is it shows the atomic number, the atomic mass, and the symbol for all these different elements that make up the matter of our world and the universe. So at least what's been discovered so far. Now, how did it exactly get to the shape? How are we actually able to see what it is? How are there trends behind it? What does that mean? So one thing about it is you might have noticed is that it's organized via atomic number, which is that as you see, it goes from 1, 2, 3, 4, and so forth across your periodic table. And even if you look at a modern example, you will see that increase. Now, that's something that did not just come from just pure out of nowhere. There were many scientists that came and tried to develop all kinds of versions of the periodic table. But the one that we really use today comes from Dmitry Mendeleev, who really noticed that there were patterns in the periodic table. Now, where exactly do those patterns come from? Well, that has to do from the properties of these different elements. One thing about the things that have been observed is that there were matching properties that were seen, right? So if we kind of see here and I map out the properties of, like, let's say helium, neon, and argon, notice how I put them all in blue. These are all your noble gases. They all have very similar properties, being all gases. Lithium, sodium, and then the next element would also all have very reactive tendencies, whereas beryllium and magnesium tend to be a little bit more stable. They're similar to one another. So the chemical properties of these different elements were similar. Now, as a result of this, being when they were able to line up all the different elements, he was able to see that, oh, what if I try to move this in a different way? We can actually see that things are starting to line up with one another, that these elements actually have, if we increase them by the atomic number, which is the protons of these things, that we're actually able to determine what are the different properties. Now, originally, this was done by mass originally, being that they didn't really know entirely about protons at the time, but they were able to line them all up by their numbers over time as it was further and further developed. So this is how all this kind of came to be. We were able to organize the whole entire periodic table via properties. So what can we see in terms of the major classifications of this? When we look at the periodic table, if we kind of organize all the little parts, the left side of the periodic table, it happens to now all be metals. every single one of these, right from, there's a zigzag generally on all your periodic tables. You'll see it as a bold line. This denotes on the left side of it, left side is all metals. So these are very good conductors of heat and electricity. They can be formed into different objects. They also lose electrons very easily as well. They're very good cations. On the right-hand side of the periodic table is where all the non-metals are, meaning that their phase can vary. They can be gases, they can be liquids, they can be solids. It's very easy for them to change. A lot of these tend to be what we see in the organic chemistry area. They also tend to gain electrons as well, so they have that tendency to gain. Now, in the middle doesn't fit on one side or the other. This is where we call the metalloids. So metalloids. So it comes right in the middle of the two different classifications, because they are very good as semiconductors, whereas like non-metals couldn't be, couldn't actually conduct electricity. The metals could. They fall in the middle. So they have a little bit of properties of both sides. They don't just fit in one or the other. So generally this area is the middle. So we classify these. Now, this helps us be able to label and predict what all these different elements can do, which is always very, very important, right? The ability to prediction is kind of what makes science interesting and lets you be able to make hypotheses, try to make scientific theory to determine what can happen. Now, going even farther, when we look at these, right, we have all those individual classifications. There's more ways we can label the periodic table too. The first thing is on the left and the right side of the table, where I kind of call them like the two towers of the periodic table. We can label as our main group of elements. So the main group tends to be where most of the chemistry in introductory chemistry and general chemistry 1 takes place. We typically like to look around here because it's more easily predictable. This is where your predictable ion charges come from. They don't really have any sort of crazy chemistry. This is where a lot of the type 1 ionic compounds are going to be born out of, which you will see in future videos or other videos. Now in the middle, this is where the transition metals are. These ones are not as predictable. This is where the chemistry can get really wild and crazy. This is what tends to be a lot of the things that are used within your cell phones as batteries, as conductors of electricity in all of our devices. They can really have a lot of different interesting properties that can be seen. This is where we refer to as type 2 metals, especially when it comes to cations being used for ionic compounds. So keep that in mind when it comes to those classifications and how we can label all these different species. Now, we have all these labels, right? Label. We like to be organized and try to discuss everything. The other thing that we also have is what we refer to as groups and periods, which is how we discuss columns and rows. To me, I always think of groups and periods as a very archaic, dated language going back to the early 19th to the mid 19th century. Generally, I like to refer to them as columns and rows a lot, but groups and periods is used across the entire world and probably will never go away anytime soon. So usually the way that we label groups and families, so columns, is there are two ways that they can be labeled. Depends on the periodic table you have. If you count every column across the periodic table, you will have 18 columns. However, depending on if you have an older or a newer table, you're going to see two labeling systems. They're both useful in their own way. If you have Roman numerals on top of the table, where it's going from 1 to 8 in Roman numerals, and it has an A next to it, that's labeling your main group elements. And then if it has a 1 through 10b, that's labeling your transition metals. Rows are what we use to really determine energy levels, what we use for electron configuration, how we can try to organize our periodic table to really be able to determine exactly what it is that we have. So all kinds of labels that are here, all of them are very useful when we're going through those. And if you kind of look at some of these, we can even look even farther, all the groups that we have when it comes to those columns, they are your families that were covered in previous videos and generally at the very beginning of the semester. So each of these columns, we can see the first one is the alkali metals. All of these are extremely reactive metals. They all have the same properties. When you move on to, let's say, the alkaline earth metals, these are different elements that are generally more stable, but they do have the characteristic of a lot of the different colors you see, like in fireworks and flames and all these kind of different potential possibilities to them. Then we have our pnictogens and our chalcogens. They have their own unique properties. Halogens are very, very reactive. And then the noble gases are something that is usually very inert and they don't react. So the periodic table is organized by those properties. And we can determine, if I tell you, okay, let's find a molecule in group 16 and or period number 2, you could find oxygen in that location. You can use it as like a way to index where everything is, to be able to call out where all those are. It's a way to be able to label and determine where you can find different species. Now, moving forward, what other kinds of patterns can we see? All right, so what patterns do we actually see in the periodic table? Let's take a look at it. So other than trying to classify the different types of elements, we can also see that there are other trends. So one of the things that we learned in previous videos is what ions do alkali metals make? And one thing you realize is that all of that entire column were +1, right? Column 1, we're all +1. Now, if I ask you, okay, what about halogens? Well, they also had a predictable charge. If you remember, that entire column was -1 behind all those individual charges. You could predict and assign all those. Now, when it comes to all of these, they all have a trend that comes with the electron configurations as well. We followed a very, very specific pattern, meaning that there is a pattern for atoms to be able to gain and lose valence electrons. The entire idea about the main group of elements was that they want to achieve the octet rule. The goal was to get to 8 electrons no matter what. So one of the things that we could see is that predictable ions have essentially a predictable number of valence electrons, meaning we could see how many electrons we want to be able to lose or gain in order to get to all those to get that octet rule, right? If we look at column 1, right, it has 1 valence electron. Well, what is the charge of column 1? If you remember, it's +1, meaning that it has the urge to want to lose that 1 electron. Now, if you go to the next column, you'll see that it's 2 valence electrons. Well, what was the charge of that column as well? It was 2+, meaning that it wants to lose those 2 electrons to help it achieve that octet rule to have a complete and filled valence electron shell. If you move across, you'll see that, oh, we'll go to 3+ and then eventually to 3-. So on the 3+, right, there's 3 valence electrons. So if we lose all 3, he'll get an octet. If we go to where it has 5 valence electrons, well, all it needs is 3 to get to 8, right? So 8 - 5 is 3. So gain 3, we can get 8. And we can see that pattern can grow as you kind of get closer and closer to 8 electrons. So there was a pattern based on the predictable charges, which is related to the amount of valence electrons that we have within the molecule, which is actually kind of cool when you see it, right? There are trends all around us. Now, what do ions have in common when we're gaining and losing electrons? There's something else that gets affected as well. So when it comes to having the tendency to make a plus charge or a negative charge, this is something that will affect the atomic size, meaning how big or small are these different elements. So one thing is that we're going to see is as you go from across the periodic table from right to left, we're going to see that the size is going to increase. Now, why does it have that tendency? So when you go first, let's start by going down the periodic table because that's usually the easiest way to see it first. I should have started there. If you remember from electron configuration, the very top left of the periodic table was 1s1, right? Right where hydrogen is. It has that 1 in front of the entire number. Now, if I go down that periodic table and I go down to lithium, which is 1s2, 2s1, the orbital is going to get bigger when it gets to 2. Now, if I continue to go down, that orbital is going to grow again to 3, and it's going to get bigger and bigger and bigger as you travel down the size of the periodic table. So one thing that we can see is that the orbital is getting larger, meaning that the size is increasing as we go down. Now, what about as you go across? Well, if I go from if I look at, let's say, carbon versus nitrogen versus oxygen, well, what can we see? What are the exact differences? Well, let's first start with the very first one, which is looking at carbon here, which has 6 protons, versus nitrogen, which has 7, and oxygen, which has 8. Now, one thing that you're kind of looking at here is we're looking at p orbitals, and we can see that they're getting smushed, they're getting a little bit closer, and getting a little bit closer as we go from left to right, meaning that they're getting smaller, right? So as you go to the right-hand side of the periodic table, they get tinier. Why is that? Well, it's because you have so many protons, they're attracting all the electrons closer and closer and closer to the center of the atom as a result. So you're going to see that there is this trend where atomic radius is going to get bigger as you go from the top right all the way down to the bottom left. It's going to get larger. So we have a trend that is here. So if I asked you like the following question as an example, and I said, okay, let's try to rank all the different atoms in their sizes that we have here. So I have gallium, phosphorus, sulfur. Can you rank them from smallest to largest? Now, if you remember our trend, right, the top right of the periodic table are the smallest. So that means sulfur would be first, phosphorus would be second, then gallium would be the largest out of them as we move across. And this is because the farther you're going down and to the left, the highest quantum number is getting bigger, bigger, bigger. And there's only maybe one valence electron, maybe 2 valence electrons that are on that outermost level. So they're not really feeling the attraction as much as other species. So this is the idea that we look at when we're looking at neutral atomic radii. Now, what about ionic radii? Well, atomic, if you remember, was neutral species. But what happens to an ion? How does the size change if you're changing how positive or negative something is? Well, the one way for us to look at it is, let's say if we want to have a cation, what exactly would happen? Well, remember this is all about the number of electrons is changing. So let's say if I take away 1 electron from you, what exactly are you going to do? Or heck, even better yet, think about it in terms of let's say if you had $5 and that's all you had to your name, and I take $1, meaning I took 20% of your money that you have. What would you do immediately? That's when we start getting cheaper. We don't want to spend any of our money. When we start seeing that our bank account's a little low and we don't really have that much. So you're going to try to hoard and bring all those closer because you don't want to lose any of them as a result. So when we lose 1 electron, the force of attraction between all the protons is going to increase because remember, electrons, they push each other away, but it's not going to be felt as much because now it's not even anymore. There's more protons, so they're going to come closer and closer together. Now with anions, it's going to be the opposite. They're going to get bigger when we put more electrons, and that's because they're all pushing each other away. Their personal space bubble is going to be too felt. It's kind of like once you get your paycheck for the week and all of a sudden you're like, oh, I'm going to buy this, I'm going to buy that, I'm going to buy this. It's like you're kind of going to be a little bit frivolous, a little less caring. You're not going to hold your money as close to yourself. We want to continue that example. So the more you have, the more repulsion. It's going to get bigger. So anions are larger, cations are smaller. So to show the size difference between those, I have a neutral atom has 0 in the middle here in gray. Pink is anion, and then the light blue is a cation. And you can see that the size difference. And if I want to increase the charge, let's say if I want to make it more and more positive, meaning I'm taking more electrons away, it's going to keep getting smaller and smaller because the nucleus is now overwhelmingly positive. It doesn't really want to potentially lose any more electrons either. So it's also going to hold everything very close. Versus an anion, it's going to get larger and larger and larger as a result. So we can really see that there is a very big difference when it comes to the sizes of all these different species. Okay. So when we're trying to look at all these different trends, we can see that as we go down the periodic table, the size is going to get bigger. And as we move from the right-hand side to the left-hand side, it's going to get bigger as well. So it's going to be going kind of in a diagonal from right to left. And then cations are small, anions are big. What other trend do we have? So there's one other one. There's one other major one that we're going to look at. And it has to do with essentially looking at ionization energy. Now break down that word, the first 3 letters, ion. So it has to do something with ions. Now, ionization energy is how easy is it for a neutral atom to lose an electron? How is it easy to be removed? Depending on your course, so in introductory chemistry, we only worry about this, but if you're taking general chemistry, you might also have to worry about electron affinity, which is the opposite. It's all about how attracted are you to an electron, but the trends still go in the same direction. So if we're going to lose an electron, this is something where, well, it's going to be easier in certain directions over another. So how exactly can we see that? Well, in terms of patterns, it's all about, well, where's the positive energy? Where is the negative energy? When you travel towards the negative side of the periodic table, so closer to fluorine in the top right, the energy to remove an electron is going to be higher because it does not want to lose an electron. It wants to gain one. So it's going to get really, really hard to pull off an electron when you have a -1 charge. It only needs that 1 electron to get a -1. So the energy increases as you go up and to the right. Essentially, the farther and farther the electron gets away from the nucleus, so the more valence it becomes a lot easier. So as you travel downwards, you can see the energy will be really, really low as a result. As you're trying to travel through, trying to look across all these different trends. Now, so let's go through and try to summarize all of these and go back to our original slide. All right, to summarize everything we talked about, so going back to the beginning, all the trends. So as we go from up into the right of the periodic table, so going in this direction towards fluorine, we will see the ionization energy increases, meaning it takes a lot of work to remove those electrons. All of these guys, if you remember, were all -1, -2, -3. There's stuff that do not want to lose them. So that's why it's so much higher. It takes work, right? Energy is something that takes effort. How easy is it for you to go to the gym or to run or do all these things? It takes a lot of work. The radius is how big it's going to get. Now notice how the trends are opposite of each other, meaning the bigger that the molecule is, the easier it is to rip an electron off. So if it's very, very large and has a lot of electrons, as we get down to the bottom to the left, right? If you think of francium, which is right here at the bottom, it has 87 electrons. So, and there's only 1 in the outermost layer. So it's going to be really easy to misplace it or lose it. So being that so far away. Now, the other trend that I did not really necessarily talk about, but is metallic character, that has to do with the characterization of the table. Remember, the left were all metals, the right's all non-metals. Well, as you go more and farther away from the non-metals, the more metallic things become. Okay, so all these are more metallic than the non-metals. Okay, So this is the general idea. It's a lot of info, but hopefully you can kind of get a basic idea that there's a lot of things buried in your periodic table. Tons of information, tons to learn. Thank you so much for listening. I hope this video helped a little bit, and I look forward to seeing you all in the future. I'll see you all later. Bye now.